Hello everyone, my name is Hamid Akhtar and today I'm going to talk about where does my insert go, a logical replication story. In this talk, we're going to start with an insert from the publisher to the subscriber database. So if you're planning on understanding the workflow of how logical replication works, this talk is for you. It will give you all the details about the wall, the logical replication, the decoding, and take you from the publisher to the subscriber. Okay, so where does my insert go? Time to look into more detail now. So here is the roadmap. On the left-hand side, you see three stops. On the right-hand side, you see three more stops. The left-hand side is really all about how a tuple is actually being written on the publisher. We start from the insert, the time the insert begins on the publisher, makes its way to the shared buffer, eventually to the wall, and how does adding, say, or changing the wall level to logical adds more detail to it, and finally, how does the publishing work? Starts with logical decoding layer, the reorder buffer comes in, which reassembles the transaction order, and then finally to the next three stops, the replication slots and the output plugins, and finally the subscriber receiving that data. So to understand this, we're essentially going to walk through all of these 9 stops, understanding what exactly is done at each stop, and then we're going to make our way towards the publisher and the subscriber towards the end. So the story begins when we receive an insert statement. In our case, as you see on the slide, insert into orders a customer ID and the amount. It's a pretty big amount, as you can see, $99.95. So what exactly happens here? Obviously, the Postgres or the publisher in this case receives this query. It goes through the parsing and analyzing and rewriting phases and the planning phase, which eventually generates an optimized query tree, which is passed to the executor. The executor in this particular case is now going to insert that query or the tuple data. But before it can do that, it needs to construct a structure which is essentially a representation of a row of that particular table, in our case, the orders table. So we're going to see that the column and the values that we provided in the insert statements are going to be transformed into something that Postgres or the table representation can understand. So it starts with some information about the header, which is essentially the visibility information and the placement information and certain flags that define the state of that tuple. So xmin is the transaction ID of the transaction that's creating this tuple. Then there's some meta information about it, the null bitmaps and the actual column data. So xmax, obviously in this case, being an insert statement is 0 because xmax represents the transaction ID that deletes or removes or updates that tuple. So now at the end of this first phase or the first stop, we now have a representation of a row as a tuple. So it's a heap tuple in this case, which is the standard Postgres table um, format. Now, what we need to do is insert this tuple into the table itself. But before we can do that, we need to essentially find a space in that table. That table can have spaces in any of its blocks where our tuple can fit in, or maybe there is a requirement to extend that relation so that we can, if there's not enough space in the table. That's where the free space map comes in. So our tuple finds a place on the 42nd page of this table. This 42nd page represents the blocks in the shared buffer. Shared buffer is the memory that's shared across all the backends. So the part of heap insert process ends up taking an exclusive block on that buffer, putting that tuple data in there, and making sure that the line pointer or a kind of a position holder marking where the tuple starts is updated. so that within that block, we can find that tuple conveniently. So after the second stop, we have that data in the table in memory in our shared buffer. It's not persistent yet. So the table headers are updated, the but still it's not crash safe yet. So we next need to create a wall record here. A wall record represents the write-ahead log record that ensures durability of this tuple. So this all should happen before we can confirm to the client or to the user that the data has been saved successfully and the transaction has committed successfully. So what happens here? We start with xlog begin insert, telling the xlog that we're actually intending to write something here and add a wall record. So once we do that, we then insert some metadata, we insert the tuple data into it, and we assemble that wall record in memory right now. Why in memory? Because so far we've not committed the transaction, so there's no way of us basically saying that this transaction is good to go. So the wall can be flushed either at specific, say, the intervals by the background writer for wall or through a commit statement. When we issue a commit statement, that's when the xlog data is actually flushed onto the disk, and that's the first time when this insert or this tuple is actually guaranteed to survive a crash. So we now have our transaction committed. We now have a tuple that's durable, that's in wall, and that is crash safe. So the anatomy of that wall record actually has some other details in it. It has information about the transaction ID. It has the information about what's known as a resource manager and some information about it. A resource manager identifies what or how or who interprets this wall record. So in our case, it's the resource manager is heap. It knows, for example, certain operations or how to interpret certain wall records. So, and now based on that data, it can understand as part of, say, xlog info that this is an insert statement for a heap. So now it can interpret that and it can actually understand or update other aspects with it. The important thing to note here is that in the wall, we don't just write the data of that tuple. In some cases, in case full page image writes is on, which by default is, we might dump the whole page or the whole 8K block to the wall. That is to prevent, again, certain crashes, which is like, for example, a torn page, um, which say, as we're writing an 8K page to the disk, we might end up crashing midway. So just writing 4K rather than 8K. So this full page image writes will protect us against those torn pages. So far, we've created a tuple. We've saved that in memory in shared buffer. We've saved that in the wall data, and we've preserved that on disk. But for us now, we need to interpret that data as column and values. There are different types of wall levels that we can set. A replica is essentially to replicate data that's in binary format, but without any specific knowledge of what that data represents. So if we've set up streaming replication, all we need to know is what data should we update. We don't care what columns or what values there are. We don't need to understand that information. All we need to know is this chunk goes where, that's what we do. So if it's an 8K chunk, the entire block, we replace the entire block. If it's the tuple data, we replace that tuple data in that block, in that place. That's all done as part of streaming replication or physical replication. But for logical replication, we also need to understand that data so that we can deal with it smartly, because we need to understand, from a logical perspective, what columns were updated, what were their values in this particular case. So if we are inserting a tuple, we need to understand the columns and their values specifically and the relation that it was part of. So there's certain additional pieces of information that are added when logical replication, for logical replication. So we have the origin information that prevents cycles. We have some markers telling the logical replication pipeline that we have new tuple as part of this data, so it can then decode it. We also need to make sure that when we're doing full page image writes, we're not actually overwriting, or we're still carrying that tuple data with it. So in physical replication, when we're doing a full page image write, we don't preserve the data for that tuple that we've just inserted. But in logical replication, we need to logically interpret that, and therefore we need that information, additional piece of information along with it. We additionally might need some information about the relation. We might need additional information whether this transaction committed or aborted, and we might need some information about the catalogs. So, in the logical decoding layer involves a wall sender process, logical decoding, and reorder buffer. Now, these are three pretty intense components of logical replication. Starting with wall sender, a wall sender gets initiated when a subscriber connects. So it's initiated by the subscriber when the postmaster receives a request to start replication, and a wall sender is launched. The wall sender is responsible for reading the wall data. It's essentially sleeping on a latch or waiting for more data to arrive, more wall data to arrive. When some wall data is generated, it's these wall senders that are waiting for that particular kind of wall are woken up. So you have separate for streaming replication and then separate wall senders for logical replication. They're woken up when their corresponding data becomes available. So they wake up, and that's when the processing starts. So remember that as part of wall writing, we added additional information for it to be logically decoded. That's not there for streaming replication. So the wall sender starts and it'll initiate the logical decoder process. But then becomes another challenge. The wall is not written sequentially it's written sequentially, but it's not contiguous for a commit. It may or may not be. So we'll come to that and see how that happens or why that happens. So what happens here is that when the wall sender sees that there's more wall for it to receive, um, it reads that wall, and then it finally sees that, oh, so this wall can be processed by this particular resource manager, RM heap in this case, and it knows that it has additional information about how that resource manager should interpret that particular wall record, which is provided in Excel or Xlog info. So it's a insert in our case. So it invokes the resource manager for heap, giving it the wall record and the info. So what happens particularly with wall? On the left-hand side, you can see that the wall is actually interleaved. You have multiple running transactions. They're doing DMLs. They're doing inserts, updates, and deletes, and they're running in parallel. So there's no way of us holding back one particular backend for another while it completes a transaction and writes all the wall contents onto disk. So the changes, the DMLs are interleaved. So on the left-hand side, you can see that you have transaction A, it performs an insert, transaction B performs an insert, transaction A performs an update, and transaction B commits. Finally, transaction A commits. Although transaction A started earlier, it commits later. Obviously, when reading the wall, The wall sender now needs to make sure that it can interpret all of this data accurately, and that's where the transaction ID that was inserted as part of the wall record comes in handy. So we have the resource manager, we have the transaction ID. So as it's reading those wall records, it's organizing that data in transaction IDs based on their transaction ID. So it's grouping them together. So that's what reorder buffer does. It's going to reorder the wall stream based on the transaction ID. And within those transaction IDs, if there are sub transaction IDs, it's also going to put them under the parent transaction ID. So you see that it's collected transaction B first, insert and commit, not transaction A, which started earlier. It's done with transaction B first, and then it's going to basically process transaction A. So more about the reorder buffer. It's, as you can see, what it does is that it creates a list essentially based on transaction ID. Um, and it's going to put everything, all the wall record, all the changes within that wall record under that transaction ID key. That's the organization. So the moment it receives um, that information, it's going to put all of that information in memory, in its buffer, and it's going to wait for a transaction boundary to come. Whether that's a commit, whether that's a rollback, that will come um, as the process proceeds on, as we receive more wall. So, but it's doing that simultaneously, or it's doing that in parallel, not waiting for the transaction boundary and then collecting all the wall records, but it's doing that along the way as the transactions are in progress. So, how or what happens internally is that it's collecting all that pieces of information, it's collecting all those changes, it's making sure that it's the moment more wall arrives, it understands which transaction it belongs to and puts that change under that transaction as a part of that structure. So the heap decode processes is going to create those reorder buffer changes, and it's a list. It's basically a queue, a process where you have all those changes. But at this point, we're not sure whether this transaction committed or aborted. Um, and it's all being done while the transaction is in progress. So finally, or eventually, when the xlog exec commit arrives, and that's the xlog info that can be handled by your transaction resource manager. It now then invokes the function exec decode. Now that's part of the resource manager um, callback function array. So the wall sender receives this commit, or and now basically it's going to go through with the decoding process. It calls decode commit, registers all the sub transactions. It reorganizes all the sub transactions because the sub transactions also need to be organized or put into the LSN order. The LSN is the log sequence number for the wall, basically the position of that wall record within the stream of wall, so that the changes are replayed in that very same sequence rather than out of sequence. So the reorder buffer is responsible for collecting all those changes. It's also then, in case of transaction commit, is responsible for shipping out those changes to whoever is listening on. The reorder buffer then essentially um, is going to invoke the decoders, the logical decoders for it, to process those changes. But it can suffer from certain issues with work mem, where if there's a very large transaction, it might end up writing to disk, it might end up costing significant IO. So that's one caveat where you have large transactions that may cause this issue. But the protocol for logical decoding provides you with a streaming option where you can stream those changes across to the standby, to the subscriber without waiting for a commit or a rollback record. So what happens is that once we receive a commit, we know that we need to send out this change to the subscriber. That's different from a physical replication setup. So it's basically going to start with begin callback. It's going to provide certain information there. And then for each change that it has collected in the reorder buffer, it's going to send out a change callback of, or call the change callback for the logical decoder output plugin. And finally, when the commit is received, it is going to send out the commit. So it detects a commit. It, for all the sub transactions, is going to do a k-way merge, trying to not sort but organize or pick up the lowest LSN values for all the sub transactions and send them one by one. So it's not going to look at or sending out all the sub transactions in one go, but see which change came in first. So you can see the signature, what the signature of an output plugin begin callback would be, where the XID is provided, the commit timestamp is provided, and that information is sent out to the subscriber. Then for each change, it's going to do a change callback where it's going to provide that information about that particular change. In our case, it's the insert into the public orders table and the corresponding data. And finally, when we reach the commit in the reorder buffer, we're going to send the XID and the commit LSN. The replication slots are there to ensure that the subscribers' data that they rely on the publisher is preserved. So the wall segments are preserved. They're not lost because for the wall cleanup policy kicks in. So they are basically your guarantee to the um, for logical replication that would ensure that the LSNs that are still required, the wall records that are still required by the subscriber, are retained on the publisher. Yes, it can lead to significant growth in the wall data, but that's the trade-off. If a subscriber needs it and the subscriber is actively utilizing it, you would not have that issue. But the subscriber really relies on the restart LSN, which tracks, say, the catalog changes that may be required. The confirm flush LSN is the point where the subscriber has made changes durable that it's received from the publisher. So the output plugins that are part of the logical decoding flow are, the standard one is PG output. You have a test decoding that you can use or understand or test in a human readable format, the output of this logical replication. And then there's a third party wall to JSON, which can be utilized by third parties or by CDC pipelines. Here is their output in simplified format. So test decoding, you can see it's clearly in a human readable format. Wall to JSON is obviously in a JSON format, which can be machine processed or by another software. And then you have PG output, which is going through the protocol for binary protocol for logical replication with a begin message, relation information, which carries the information about the OID of that relation, the columns, its data types, and everything that you need to know about that relation. Insert message, in case of update, you would have old and new values, and the commit message finally. So that's your protocol for output. On the apply side, we're receiving these protocol messages from the publisher with begin. So on the subscriber, we end up creating a subscriber transaction. We start receiving all the changes, then we apply those changes locally. And remember, these are not binary changes. These are logical changes. So we receive the table name, the column, and the value. So we're making those changes ourselves by applying those heap changes ourselves here. So we end up making that change in the orders table. We commit it locally, and after that's committed, we update the REPL origin LSN, which is then sent back to the publisher, telling it that this is the LSN that we have made durable on the subscriber. So our tuple started with a SQL statement. The heap tuple made its way into the memory, then to physical wall record, then as part of a logical decoding change. Finally, it made its way to the logical or the reorder buffer queue, to the output plugin, which then decoded the ordered reorder buffer and sent messages to the subscriber, and finally the subscriber implementing those changes on its side. So the complete set of stops that we have are insert statements, the executor, which creates the heap tuple, the shared buffer, which is the table in memory, essentially, or part of that in memory, the wall buffers, the wall on disk, the wall sender that performs the decoder process or initiates it, the reorder buffer, which organizes your commit and all the changes in a set, the replication slot, which ensures that the data that is required by the subscriber is not lost on the publisher. The output plugin sends out the changes to the subscriber, and the apply on the subscriber applies those changes. So we have the physical path, which is really the executor and the buffer and the wall. The logical path, which is decoding, reorder buffer, and output plugin. The wall level, which adds additional information. Reorder buffer, which organizes all the wall records and emits them in the order so that it can be committed in that in an LSN sequence order. Replication slots ensures guarantee that no changes are lost. Output plugin is basically an extension, an extensibility layer, which by default provides logical replication. And obviously, like in most observability issues, long-running transactions would be a challenge, would hold back a lot of this process. That's all. So thank you so much. Here is my contact information, and you can also find me in the Discord channel in case you have any questions. I know this has been a lot of details, a lot of information, so feel free to reach out to me in the Discord channel. Thank you.